So DNA had been known to exist on chromosomes since the last part of the 19th century. It was only in 1944 that there was sort of almost definitive evidence that DNA must be the genetic molecule. This key experiment occurred in the Rockefeller Institute for Medical Research in New York, in the laboratory of Avery. And what they showed was that you could change the heredity of bacteria by mixing it with pure DNA. And the specificity of the bacteria would correspond to that where the DNA came from. And this was published in 1944, but it wasn't to great acclaim. At that time, most chemists were interested in proteins as opposed to nucleic acids, because it had been shown that proteins carried enzymatic activity. They were functional. So most of the chemists studying cells focused on proteins. We called these people biochemists. And the number of people working on DNA compared to proteins was maybe 1%. And so they didn't like the idea that what they were working on wasn't also the genetic molecule. But if you didn't have a prejudice and just looked at the experiment, the Avery experiment was Avery and McCarthy and McLeod. Certainly when I first became aware of the experiment, at the time I went to graduate school in '47, it looked right. It had the smell of being right, but the general community was still protein dominated. I was originally trained to be a naturalist. I was interested in birds and thought my career would be that of going out and studying nature. But in the spring of 1946, I read a very influential book called What is Life by the great German physicist Erwin Schrödinger. During the war, he had escaped from Hitler and was living in Ireland and gave 3 lectures at Trinity College, which were put together in a small book. And he asked the question, what is life? And he came back and said, the essence of life must lie in a molecule which carried the information, which, say, made a cell of bacteria, or made a fly, or made a human being. You know, one had just thought life was enzymes. But he emphasized what, of course, had been known to geneticists, that key was information. The information to be a fly, or to be a human being, or to be a man, or versus a woman. Where did that information reside? And the famous Avery experiment said it resided in DNA.
Nonostante l'ereditarietà dei caratteri abbia interessato e stupito l'uomo da sempre, è solo a metà Ottocento che con gli studi di Mendel si è iniziato a capire il suo funzionamento. Si sapeva che tutte le piante e gli animali erano costituiti da cellule, ma solo verso la metà del secolo furono disponibili microscopi sufficientemente potenti per poterle finalmente esaminare. Si rivelò così la loro complessità e si vide che oltre a produrre una propria energia, secernere sostanze chimiche e trarre nutrimento dall'ambiente, le cellule potevano anche riprodursi. I biologi scoprirono che le cellule si riproducono dividendosi in due. Al centro di ogni cellula si trova un nucleo. Prima che la cellula si divida, il piccolo nucleo sembra dissolversi. Molti filamenti sottili diventano visibili e si dispongono uno di fianco all'altro in coppie. I fili si assottigliano. La cellula diventa talmente sottile al centro da assomigliare ad una clessidra e alla fine si divide in due. I filamenti contenuti in ciascuna cellula si ricondensano nelle due nuove cellule fino a formare un nuovo nucleo. Solo verso la fine dell'Ottocento i biologi si accorsero che ognuna delle nuove cellule conteneva un numero di filamenti identico alla cellula originaria. Siccome per individuare i filamenti si aggiungeva un colorante alla cellula, i filamenti presero il nome di cromosomi, dal greco corpi colorati. Una cellula è a tutti gli effetti una entità vivente e prima di morire riproduce una copia di se stessa. Un passo decisivo fu capire come avviene la riproduzione nella specie umana. La presenza degli spermatozoi era conosciuta fin dal 600, ma solo nel 1827 uno scienziato tedesco scoprì che esisteva un equivalente degli spermatozoi nelle donne, gli ovuli. Fu allora che si capì che la prole derivava dalla fusione in un'unica cellula di una cellula spermatica maschile e di un ovulo femminile. Negli esseri umani, una normale cellula del corpo possiede 46 cromosomi. Negli ovuli e negli spermatozoi ce ne sono 23. Quando uno spermatozoo e un ovulo si uniscono, contribuiscono alla nuova cellula ciascuno con 23 cromosomi. Fu questa osservazione a far supporre che fossero i cromosomi gli elementi che contenevano i caratteri specifici che si tramandano di generazione in generazione.
So I was focused on DNA from almost the first time I read about the famous Avery experiment. I wanted to know about it. But through classes, you can learn very little because there wasn't much to be known. Even though the Avery discovery had looked like it was right, and should have led very soon to a Nobel Prize, the number of people working with DNA was very small. And where I was doing my PhD, no one was working on it. For my PhD thesis, I studied the viruses of bacteria. Viruses, now we realize them to be little packets of genetic material of DNA surrounded by a protein which can move from one cell to another. And when they get into an uninfected cell, they multiply to form large numbers. I wanted to work on bacterial viruses because they seem to be the simplest system to study DNA in operation. In 1947, when I went to Indiana University, the most famous person working with bacterial viruses was the German-born physicist Max Delbruck, who'd been a theoretical physicist associated for several years with Niels Bohr in Copenhagen. And then he had moved to Berlin, where he had met a Russian-born geneticist, Timofey Rozevsky, who was using X-rays to try and determine the size of the gene. The argument is simply that if the gene is very small, you'll only be able to inactivate it if you use a very large amount of X-rays. Or if the gene is big, you use less. So you can do calculations of the density of ionizations produced by X-rays. So, and if you say every ionization knocks out the gene, you could then get the size of the gene. It was called target theory. And Delbruck was intrigued by it, and he and Timofeyev and a German physicist, Carl Zimmer, wrote a paper in 1934 saying this is one way maybe to begin to get the size of the gene. And Delbruck's paper was noticed by Schrödinger, and it was really Delbruck's ideas that formed the core of Schrödinger's book, What is Life? When I got to Indiana, I discovered that the member of the faculty I really wanted to work with, Salvador Luria from Italy, had been doing experiments jointly with Delbruck for the last 6 years. And there was a tiny group of people that was called the phage group. They were using these bacteriophages as the simplest system to try and get at the essence of the gene. And if they'd been chemically purified, and about half their mass was DNA. I had the good fortune during the summer of 1948 of being here in Cold Spring Harbor. Luria came here, and Delbruck came here, and they were doing experiments, and so I met Delbruck. With us at that, with Luria was his new sort of collaborator, Renato Rebecco, that joined him in the fall of 1947, coming from Torino. Both had obtained their medical degree at the university in Torino. But during the course of the 3 years I was working on my PhD thesis, you sort of counted the number of phage particles, but no one talked about DNA. And I guess the reason was that the phage group was deficient in chemistry. They were either MDs or they were physicists. And to get at the structure of DNA, it was a problem in chemistry. And there was a sort of snobbery. The most intellectual field in biology was genetics, and the most intellectual field in the physical sciences was physics. And chemists were thought to be necessary but dull. And they were wrong. The essence of genetics had to come out of chemistry. It never came out of physics. But that was for us to find out later. So Delbruck had been greatly influenced by being in Copenhagen, so I thought when I finished my PhD, I should go to Copenhagen. So I did. And I was told someone was going to work on the biochemistry of DNA. But when I got there, he wasn't working on the biochemistry of DNA. He wasn't really interested in DNA. And sort of by just great luck, my sort of supervisors decided to be in Naples during April and May, and I went along and was at the Stazione. And I wasn't doing experiments, I was just reading in the library. I like to read. But toward the end of my visit, there was a tiny meeting. It was sort of on the structure of the big molecules of cells, macromolecules. And there was a talk on DNA. by a young English physicist, Morris Wilkins, who showed that DNA we put in the beam of X-rays diffracts in a very regular fashion, as if the DNA molecules came together to form a regular crystal. So if they formed a crystal, DNA must have a very regular structure. And until that moment, a piece of DNA would represent a different gene, and they'd all have different structures. So suddenly I realized there was a general structure for the gene, which could be found if we found, solve what is called the X-ray diffraction diagram, and were able to interpret it. And so when I went back to Copenhagen, I wrote to Salvador Luria saying, I want to get out of Copenhagen and go to England and really focus on DNA. And Luria really changed my life, because he went to a meeting at the University of Michigan and met an English chemist who was working on X-ray diffraction at the famed Cambridge University. And he learned that the Englishman wanted someone to help him. And Luria said, my student Watson wants to get into X-ray crystallography because he eventually wants to do DNA, but he'd be happy to work on protein to start with. So I went to Cambridge in the beginning of October of 1951. And expecting that I would spend a couple of years learning the techniques of X-ray diffraction so that I could take X-ray pictures of DNA myself. But within such a day of my arrival, I realized this was not what was going to happen. Because John Kedrew, he said, you really enjoy meeting Francis Crick. That was a young English physicist who was working in the same small group at the Cavendish. We were working in the physics laboratory. And we were really in a physics laboratory because we really needed a very good source of X-rays, much better, and so needed to be near the high technology of experimental physics to get the apparatus we needed. So their objective was to get the three-dimensional structure of hemoglobin and its smaller cousin myoglobin. There was the Austrian-born Max Perutz, who had come to England in 1936 from Vienna and never went back. He was Jewish. And he stayed in Cambridge, and then when the war was over, he'd had enough progress so the Medical Research Council of England decided that they would start a small group devoted to the three-dimensional structure of the biologically important molecules. And it was that group I found myself part of. It had 6 people in it, I was the 6th person. The lead physicist, Sir Lawrence Bragg, who got the Nobel Prize in 1915 for really establishing the general principles by which you can use X-ray analysis to solve molecules. He and his father had this clever idea that's known forever as Bragg's Law. And the hope was that a sophisticated use of Bragg's Law could lead you to the structure of proteins, and in my case, would lead you to the structure of DNA.
La cellula contiene 46 cromosomi per trasmettere i caratteri ereditari. Ma questo è un numero insufficiente a rappresentare tutte le caratteristiche di un essere umano. Dunque i cromosomi dovevano essere costituiti da centinaia o migliaia di particelle contenenti i caratteri ereditari. Nel 1909 queste particelle ereditarie furono battezzate geni, che in greco significa origine, e da lì viene il termine genetica, la scienza che studia le caratteristiche degli esseri viventi. Nello stesso periodo in cui si individuarono i geni, lo scienziato americano Thomas Morgan scoprì, tramite studi sui cromosomi di un particolare moscerino, il Drosophila, che i geni erano parte dei cromosomi. Nel moscerino utilizzato per gli esperimenti, infatti, i geni erano individuati come strisce scure nei cromosomi. Il passo successivo fu scoprire di cosa erano fatti i geni, i quali erano sicuramente costituiti di atomi, come ogni altra cosa in natura. Ma quali erano questi atomi e come erano disposti? Al microscopio i geni si presentavano sotto forma di sottili filamenti, il che faceva supporre che queste molecole potevano essere formate da migliaia di atomi collegati l'uno all'altro in una lunga catena. Genetisti e chimici individuarono che la sostanza che formava questa catena era l'acido desossiribonucleico, il DNA. Una molecola dalle dimensioni impressionanti, formata da miliardi di atomi. Si pensi al paragone con una molecola d'acqua che è composta di 3 atomi, 2 di idrogeno e 1 d'ossigeno. La molecola di DNA contiene carbonio, ossigeno, zolfo, fosforo e idrogeno, combinati in modo da poter immagazzinare tutte le informazioni necessarie per dare origine all'essere umano. I geni sono quindi sequenze di DNA che specificano determinate caratteristiche.
So for my first day in Cambridge, the chief topic that I heard over and over, the chief word, was helix. That these big, long, linear molecules would fold up as a helix. And so it was thought the polypeptide chains, which make up proteins, had a helical fold. And I wondered, did the long DNA chains, did they also have a helical fold? Now, the Cambridge people, before my arrival, had sort of tried to guess as chemists what would be the best structure for how a polypeptide chain might fold up, and published a paper on it. And then, to their horror, that almost as soon as they had put forth their ideas, a paper appeared from California, from the California Institute of Technology, where the lead chemist was the head of the chemistry department, Linus Pauling. Then perhaps the most famous chemist in the world, who had written a very influential book called The Nature of the Chemical Bond. And the key bond which links amino acids together in polypeptide chains is called the peptide bond. And Pauling had, from X-ray studies, deduced that the peptide bond was flat, it didn't rotate. And if he put that into his model, he ended up with something called the alpha helix. And from the moment the Cambridge people saw Pauling's paper, They were very dejected. The alpha helix was just chemically it just looked right. And Perouse quickly did an experiment which confirmed it. And so when I was there, we knew that Pauling was right. So the question was, could you, if you were a good chemist, could you do what Pauling had done for the polypeptide chain for the DNA chain? How should the DNA hold up into a helix? And my first day there, I went to a pub for lunch with the 35-year-old Francis Crick. I was then 23, so he was 12 years older than I, and had been in Cambridge when I arrived for 4 years, but 2 years he was in a biology lab and he got nowhere. He wanted to, do something fundamental. And so thought it would be the best way to advance his career would be to work on the three-dimensional structure of proteins. So once we met, we began to talk about, could we make a three-dimensional model of DNA and get the structure of DNA without doing any X-ray diffraction work. Pauling had done no experimental work to get the structure of the polypeptide, but just was a good chemist. Now, of course, the problem was neither Crick or I were chemists. And so almost from the beginning, I decided to learn everything in Pauling's book, The Nature of the Chemical Bond, figuring that maybe in that book would be some clue as to what we could use. And then it turned out that Crick was a good personal friend of Morris Wilkins, the young physicist that I met in Naples. And so Crick invited Wilkins down for a Sunday lunch, which Crick's wife talked, and I was there, and we learned that Wilkins had almost stopped working on DNA because his boss, Professor John Randall, had hired a young woman's chemist, Rosalind Franklin, and they had decided that she knew more about X-ray diffraction techniques than Wilkins, and so she should be put in charge of the DNA project. And Wilkins said she was soon going to give a talk on her new estate, and I should go to London, and I did, and when I heard it. And not being a chemist, I didn't really understand what she said, but came back and told Crick what I thought she said, and we actually tried to build a DNA molecule. And there was an argument from the density that there would probably be 3 chains. So we tried to build a molecule which had sort of 3 wires going up, twisted around each other. And we put the phosphate atoms, which are sort of link the units together, in the center, because we thought they're regular. So there was a regular component to DNA called the sugar phosphate backbone, and then there were the 4 building blocks: adenine, guanine, thymine, and cytosine. Which the best guess was they would have a different structure for every gene. And so, since they would vary from one DNA molecule to another, you shouldn't use these to try and form a regular repeating unit. Now, in the end, we discovered that was a bad argument, but we built a structure which turned out to be just awful. And the people in London didn't like the idea of people in Cambridge competing with them, using the data of London to try and beat London.
La scoperta della doppia elica del DNA diede il via allo studio dei meccanismi che stanno alla base della conservazione e delle modificazioni delle istruzioni biologiche contenute nel patrimonio genetico di ciascun individuo. Sono proprio le nozioni che mancavano a Darwin e che sono state poi introdotte a poco nella teoria evoluzionistica. Nessuna di queste nuove acquisizioni ha stravolto l'originale visione darwiniana e semmai la biologia di questo secolo ha condotto a sorprendenti conferme. Ogni cellula di un organismo contiene il patrimonio genetico caratteristico della specie a cui l'organismo appartiene. Questo patrimonio genetico è portato dai cromosomi delle varie cellule sotto forma di un nastro di DNA. Il DNA si presenta come un lunghissimo messaggio scritto in un alfabeto di sole 4 lettere: A, G, C e T. Le lettere rappresentano le 4 basi azotate dette nucleotidi che costituiscono i pioli della scala a chiocciola della struttura del DNA. A è l'adenina, G è la guanina, C è la citosina, T è la timina. I nucleotidi sono raggruppati a 2 a seconda della struttura. Adenina e guanina, contenenti 2 anelli azotati, e citosina e timina, che ne contengono solo uno. Ciascun nucleotide, per come è fatto, si può legare solo con un altro. Così la timina si lega all'adenina tramite 2 legami a idrogeno e la guanina si lega alla citosina tramite 3 legami a idrogeno. Nel costruirsi, la struttura assume una rotazione elicoidale tipica della scala a chiocciola, con i gradini costituiti dalle coppie di basi azotate e con le ringhiere fatte di fosfati e zuccheri. I 2 filamenti, le ringhiere della scala a pioli, si svolgono in senso contrario. Così risulta che le 2 sequenze di basi attaccate ai filamenti sono perfettamente identiche e corrono in verso contrario. Le molecole di DNA sono lunghissime. Può sembrare incredibile, ma ogni cellula umana contiene oltre 1 metro di DNA. La flessibilità di queste molecole fa sì che possano ripiegarsi su se stesse moltissime volte, in modo da poter raggiungere un volume piccolo come quello del nucleo di una cellula. Così come tante idee geniali nella storia della scienza, la struttura a doppia elica del DNA è semplice ed elegante. Pur nella sua semplicità, questa scoperta fugò immediatamente ogni dubbio circa il meccanismo di duplicazione del codice della vita.
So Crick and I were told to stop work on it. And so I moved back to viruses and worked on the structure of tobacco mosaic virus, which I proposed was a protein component had a helical arrangement of polypeptide chains. And there I was right. And, you know, I published a paper which, you know, didn't solve the structure, but, you know, it showed that I was doing something, and it made it actually a good step forward. Well, we were sort of frustrated that, you know, we weren't chemists, and there was something missing. Our fear was that Linus Pauling would himself move from proteins to DNA and try and solve the DNA structure. We were greatly relieved. In the spring of 1952, he was supposed to come to a meeting in London and talk about his famous alpha helical fold of polypeptide chains. But he never arrived because the State Department wouldn't give him a passport. They decided he was too sympathetic to the Russians. And so for political reasons, Pauling couldn't leave the United States. And we were happy because that meant he won't come to London and learn the data in London on DNA. 4 months later, he got a passport to go to the International Biochemical Congress in Paris. And it was there that I actually met him. And we both talked about that we were interested in DNA. But Pauling was still, it was clear, was focusing on proteins. And then a good piece of luck, he sent his son Peter to Cambridge to get his PhD. So from every time Peter got a letter from his father, where we were just curious, had Linus moved his attention to DNA? And then one day the terrible news came. Peter came in and said that his father had started working on DNA and had a structure for it. And we wondered, he doesn't know the data in London. Can he guess it without the data? One day Peter Pauling walked in and said he just got from his father the manuscript, which described his father's proposed structure for DNA. And so he gave it to me, and I nervously read it. And then there was something very funny. Linus Pauling had formed weak bonds called hydrogen bonds, which we knew were going to be there. But he'd used the phosphate groups, the hydrogens, and he had treated DNA as if it wasn't an acid. We didn't think there would be any hydrogen atoms there. So upon reading it, quickly just took the manuscript, went to Alex Todd, the Cambridge great chemist, and said, Pauling's manuscript looks crazy. Do you agree it's crazy? And he said, yeah, it's crazy. So we were very happy. Pauling, like us before, had decided to make a 3-chain structure, held together by bonds between phosphate groups. And it was just an ugly structure. The atoms just didn't fit together very nicely. And so I thought I should just take the manuscript into London and tell Wilkins and Rosalind Franklin that they should relax. Pauling's efforts were wrong. And the first person I talked to was Rosalind Franklin. And she didn't want DNA to be a helix. So then Morris Wilkins came in, and I gave him the manuscript. I said, look, it's great news. Pauling is wrong. And I said that Rosalind had almost physically threatened me because of my saying, talking about possible helices in DNA. And he said, I'll show you something. So he went into his room, opened the drawer, and took out an X-ray photograph of DNA I'd never seen before. So the DNA had 2 forms. It could crystallize in 2 ways, A form and B form. And the B form was Oh, it just said helix. I said, it's a helix. Oh, yeah, it's a helix. So Pauling was right on that. It was a helix. And I said to Wilkins, you should just build models. You know, someone's going to tell Pauling that he was a bad chemist, and Pauling will feel humiliated, and then come up with the right answer. And Wilkins said, Rosalind Franklin is going to leave our lab, and I will be in charge of DNA in about 3 months, and when she leaves, I will build models. And I said, you shouldn't wait. So I went back to Cambridge and reported this to Sir Lawrence Bragg, the head of the Cavendish. And he, of course, was happy that Pauling had failed. Bragg and Pauling had competed back in 1928 on the structure of silicas, and Pauling won. And then they competed on the structure of the polypeptide chain, and Pauling had won. And so Bragg wanted England to win. And so he said that Crick and Y should begin building models again. And I had, by reading the literature, had concluded that the structure was more likely to be 2 chains rather than 3, because Pauling hadn't taken into account the amount of water. If you took the amount of water, it fitted better too. And Crick told me that just put the phosphates on the outside, not on the inside, because Rosalind Franklin's X-ray pictures of the A form really said they were on the outside. We never really saw her data, so we sort of knew her reasoning. So I began building models, 2-chain models, but how did we put the bases together? If they could have any sequence, there was something strange. And so there was a piece of experimental data that Pauling had ignored, which said that if you measured the amounts of the 4 building blocks of DNA, 2 of them, adenine and thymine, were always present in the same amounts, and guanine and cytosine. So there was some chemical regularity that we should use in building the molecule. I initially didn't use it, because if you looked at the data, it wasn't 1 to 1. They were sort of 1 to 1.1 or something. So maybe this data, which came from New York City, Columbia University, and Irvin Chargaff, was wrong. But then there was a real piece of luck, is that I was trying to put like with like, adenine going to adenine and so on. And there was a chemist in the room who had trained under Linus Pauling, and he was in Cambridge for 1 year, and he was totally not interested in DNA, but when he looked at me, he said, you got the chemical structures of guanine and thymine wrong. You put the hydrogen atoms in the wrong place. Now, I just had copied it out of textbooks. But he said, all the books are wrong. And so the next day, I changed the locations of the hydrogen atoms. It was a Saturday morning. I went in maybe around 9:30. And suddenly realized that I could build a beautiful pair. So putting together adenine and thymine and guanine and cytosine, and they were the same shape, and you could build a double helix, I thought. And Crick came in and saw my base pairs and said, that means the chains, if you build this structure, the 2 chains have a direction, and they move in the opposite direction. One goes up, one goes down. And Crick had deduced from something that Rosalind Franklin wrote about the symmetry of the molecule, the DNA had two chains going in opposite directions. So she didn't know how to interpret the crystallographic data, and Crick did, and so it was clear about 11:30, and then it just seemed so perfect because the sequence of the bases on the two chains would be complementary. So if you knew the sequence on one chain, you knew by the base pairing rule the sequence on the other. And all you had to do was to separate the two chains, and each would serve as a template for building the other. So we thought, this solves the fundamental problem that Schrodinger had raised. How do you copy genetic information? Because in a cell, they're not monks, little monks copying the thing. It happens spontaneously. The chemistry likes to copy DNA. Well, why? You know, we've solved the DNA structure and we've came up with the mechanism by which it's copied. And I wrote a letter then to Delbruck in Caltech and said that we think we've solved the structure of DNA and it has unique features which probably underlie how the molecule is copied. And Delbruck was working at Caltech, the same place as Pauling, and they knew each other. And I said, don't tell Pauling. You know, we want to feel more sure. But Delbruck, upon seeing it, immediately went and told Pauling. The idea was so simple and so powerful that he couldn't not tell Pauling. And but Pauling didn't believe it. He's, you know, but Pauling came a month later to Cambridge, saw our model, and conceded, said we had it. There were probably two reasons we got to the finishing line. I was more interested in what DNA was than any person in the world. That was my life's objective. I didn't care about anything else then. And Crick was supposedly working on proteins, and he also knew it was important. So we knew we should stay in the race. It was too important one not to be in. And then we just had this tremendous piece of luck that in the same room, on the desk next to us, was perhaps the one chemist besides Linus Pauling who could have told us that those structures, the hydrogens were in the wrong place. Crick says that he never thought about that we would, become famous afterwards, but W was so pretty that, sometime we were going to get a Nobel Prize for it. Once we had the model, we knew we had to tell the people in London that we had something that probably solved their problem, and so our colleague John Kendrew called up Morris and said, Crick and Watson have a model which just might be right, you should come and look at it. Before Wilkins came out, Crick and I talked about it, and I said, we would have never solved the structure if Morris hadn't shown me that B form of DNA, and if we didn't know the data from King's. And so his name should be on the paper. And so when Wilkins came out and he looked at it, it was right. And it was just too good and too pretty not to be true. And he said, well, he'll think about putting his name because he hadn't found the structure, but we thought that would reflect history best. His name was there. And of course, we also knew that probably, we would get a Nobel Prize. But Wilkins, it would be so unfair if he wasn't included it. But the next day he called from London to say that he had talked to his non-collaborator, Rosalind Franklin, and told her about our double helical model, and that each of the Wilkins would write a paper on his work, and Franklin would write a paper, and then we would write another paper with the model, so there would be 3 papers. And that's what it turned out to be. And so Wilkins' name was never on our paper. We didn't know that Rosalind Franklin was even thinking about a helix, but after I had seen her in London, she was going to give up working on DNA and was looking at this B form, and they come to the conclusion it was a helix. Then, only 4 years later, Rosalind Franklin developed ovarian cancer and quickly died. Then, when there was finally discussions of a Nobel Prize for the DNA work, Sir Lawrence Bragg argued that Wilkins should be part of it, and so all 3 of us did get the Nobel Prize. Wilkins, many years later in his autobiography, said the biggest mistake of his life was not putting his name on the paper. I think we at least, had not wanted to be known as someone who stole his data. I wrote subsequently in my book, The Double Helix, because I thought the true story should be told. What actually happened. So initially both Crick and Wilkins really thought the only thing that was important was the final answer, not how you got at the answer. But I thought it's too good a story. So I wrote it, and afterwards Crick agreed, that the story should have been told, and it didn't hurt him.
Il codice genetico, o genoma, si può paragonare a un libretto delle istruzioni per la definizione del patrimonio genetico di un individuo. Ma come vengono scritte e poi lette queste istruzioni? I geni, segmenti di DNA, contengono le informazioni per la sintesi delle proteine, cioè le sostanze fondamentali per la costituzione di un essere vivente, dai capelli alle unghie. L'informazione genetica deve essere innanzitutto trasferita dal DNA ad una molecola con un ruolo intermedio, l'RNA, l'acido ribonucleico, che è molto simile al DNA. Anch'esso, infatti, è costituito da sequenze di 4 basi azotate, dove rispetto al DNA la timina è sostituita dall'uracile. È l'RNA che interviene nella successiva sintesi delle proteine. Le proteine sono costituite da catene di amminoacidi. Gli amminoacidi necessari per costruire qualunque proteina sono 20. Ma come fa l'RNA a sapere quali proteine dovrà sintetizzare? Durante un processo che prende il nome di trascrizione, le informazioni contenute nel DNA vengono trascritte in una molecola di RNA. L'informazione genetica così acquisita dall'RNA servirà per la sintesi delle proteine. Fu il fisico statunitense George Gamow che ipotizzò che ciascuno dei 20 amminoacidi fosse codificato da una tripletta di basi azotate. Le triplette di basi che codificano gli specifici amminoacidi sono chiamate codoni. Questi, tutti insieme, formano il codice genetico.
initially afterwards, you know, once the papers were published, we just went on. And there was the big unsolved problem. DNA was a genetic material, it copied by base pairing, but how did it order the amino acids and polypeptide chains? The order of the bases in DNA had to be used to order the amino acids and proteins. And so there was 20 amino acids and only 4 bases. So there had to be combinations. And that this was true was first formally noticed by the great theoretical physicist George Gamow, who was a good friend of Delbruck when they were in Copenhagen. And Gamow worked in Washington, D.C., and Crick came after we found the DNA structure and spent a year in the Brooklyn Polytechnic Institute, which was a center then in the United States for X-ray studies. And Crick and Gamow met. And so it was, Gamow proposed a code. There was really no evidence, just that it was a clever. Crick quickly disproved it. And we formed a club called the RNA Tie Club, connected to people who wanted to solve this combination problem. What was the nature of the genetic code? It turned out that there was just no way that, no matter how smart you were going to guess it. The answer had to come from experiments. And there was another complication, is that proteins are made in the cytoplasm, but DNA is always separated from the place by a membrane surrounding the nucleus. So there had to be a second molecule. The information had to be transported to a messenger, which took the message from the nucleus to the cytosynthesis. And when it was finally found, it was called messenger RNA. But this scheme by which information in DNA is copied into RNA, and that could be done by the same way. RNA had basically the same structure as DNA, one thing. And I've spent a couple of futile years trying to guess the structure of RNA. And I got nowhere, so I was pretty unhappy. So, it should have been a really happy time. I found the double helix, but no, I was stuck. I couldn't move on. And then it turned out there was just no way you could guess the structure. And so it wasn't as if I failed, but I maybe spent too much time failing. And so I got a position at Harvard University, and then I decided we'd have a lab which just studied making proteins in cell-free systems, to see if you could dissect it. And for a couple of years, it was very dull. And then in 1960, we discovered the the messenger RNA. And so we knew the basic scheme, but we didn't know the code. We were in Moscow for an International Biochemistry Congress. And there was a paper by Marshall Nirenberg. No one had ever heard of him. And he was studying synthesis of proteins in broken up cell extracts, and found that if he added an RNA molecule composed only of the base letter U, it produced a polypeptide chain which only had the amino acid polyphenylalanine. And then a couple months later, Crick, with his very talented collaborator Sidney Brenner, did an elegant genetic experiment which said that it's groups of 3. It's not sometimes 2, it's sometimes always groups of 3. If you have 3 bases, it's 4 times 4 times 4, 64. 64 different combinations of 4 bases taken 3 at a time. So there are 64 slots we had to fill in. And they were all filled in by June of 1966. And 3 of the coding things didn't say amino acid. They said, stop making it. Then we worked on the problem. How do you start? What's the signal to start reading a message? And my lab at Harvard did an experiment which showed that the start was always with the amino acid methionine, and the start signal was not a simple one. In case by 66, the sort of what could be called the heroic phase of molecular, but first heroic phase where there were very few people interested. Even after the discovery of double helix, most people didn't work on DNA. A couple people would join us every year. But a couple joining us by 10 years, we were up to a world of a couple hundred people.
La scoperta della struttura del DNA nel 1953 aprì la strada ad una serie di applicazioni scientifiche e tecnologiche fino ad allora impensabili, che hanno sensibilmente modificato alcuni campi della vita di tutti i giorni. Una di queste è l'impronta genetica, una tecnica che permette di identificare un individuo a partire dal suo DNA. Messa a punto negli anni '80 dal genetista inglese Sir Alec Jeffreys, l'impronta genetica si basa sull'individuazione di sequenze ripetitive di DNA, note come mini-satelliti. E proprio come le impronte digitali, i mini-satelliti identificano univocamente un individuo. Una prima applicazione di questa tecnica innovativa ha investito l'ambito della medicina legale, rivoluzionandola. Anche la più microscopica traccia rinvenuta su una scena di un crimine, come capelli o fluidi corporei, permette di ricostruire il DNA di un individuo e quindi di confrontarlo con quello degli indiziati. Anche in campo medico ed agricolo, la ricerca fece passi da gigante e negli stessi anni '80 vide la nascita delle moderne biotecnologie. Grazie alla tecnica del DNA ricombinante messa a punto negli anni '70, divenne possibile ottenere nuove sequenze di DNA dalla combinazione di materiale genetico di origini differenti. Nacquero così gli OGM, ovvero gli organismi geneticamente modificati. Uno dei primi OGM brevettati fu l'insulina sintetica. Indispensabile per le persone affette da diabete, l'insulina prodotta fino ad allora per il trattamento della malattia proveniva quasi esclusivamente dal fegato dei maiali. L'avvento dell'insulina sintetica garantiva una produzione praticamente illimitata dell'ormone e una sua perfetta corrispondenza a quella umana. In campo agricolo, la produzione del golden rice, un tipo di riso geneticamente modificato per contenere vitamina A, ha contribuito a combattere le gravi malattie legate alla carenza di questa vitamina nell'alimentazione degli abitanti di paesi come l'Africa e il sud-est asiatico. Tuttavia, fin dalla loro nascita, gli OGM sono stati oggetto di controversie. Una delle argomentazioni principali si concentra sulla possibilità che la manipolazione del DNA degli organismi possa comportare nel lungo termine delle conseguenze impreviste nella loro interazione con le altre specie viventi e quindi sull'ambiente.
And We then knew how the information goes from DNA to protein. And at that time, there was this big meeting at the Cold Spring Harbor Laboratory on Long Island called the Genetic Code. And on the last evening, we celebrated the 50th birthday of Francis Crick. So it was 13 years after finding the DNA structure. First 13 years of the DNA world was completely pure science. We never saw any practical application. We were just discovering the laws of nature. When I came and gave the first big talk on the DNA structure, the famed physicist Leo Szilard was in the audience. And he asked me, were we going to patent the double helix? And he said, no, it's just, a fact of nature. And, but Leo had made money by a patent on a method of refrigeration with Albert Einstein in Berlin in the 20s. So Leo was very, he had no job, so he actually, wanted royalties for patents. And then we talked, could you patent the design or copyright the design of the double helix? But that was just a virtually nasty idea. This was, we weren't going to make any money from DNA. That wasn't it. The object was, the double helix made Crick and I famous because it was a big advance in science. We lived in a world where we didn't think about commercial products. But suddenly in 1973, a big discovery occurred which opened up the possibility that DNA would have commercial consequences. And this was a discovery which was called recombinant DNA, that people have begun to understand, the chemistry of DNA, or the biochemistry of DNA, and had come up with ways of cutting DNA molecules at specific points. You could say we had scissors which would cut DNA. And then there was joining enzymes, so you could cut and join. So you could, if DNA was a circle, you could cut the circle and rejoin the circle. So in 1973, Herbert Boyer and Stanley Cohen, an experiment done in near San Francisco, or around San Francisco, produced the world's first recombinant. They mixed together two DNA molecules, cut them, and then got rearranged DNA. So, and this opened up the possibility that you could, if you had the right pieces, you could produce DNA molecules which could make commercially interesting products. That is, if you took the gene that coded for the amino acids in insulin, you could insert that into a tiny bacterial chromosome, move it from one bacteria to another, which we had the technique. So the techniques of bacterial genetics were fairly sophisticated then. And you ought to be able to make any molecule native molecule you wanted in a test tube if you could just isolate, say, the gene for insulin. The discovery was in '73, and 3 years later, Boyer helped form a company called Genentech with the object of making insulin in a test tube. Before recombinant DNA, insulin was made by just isolating the livers of pigs. There was always a limitation. If you could move to the test tube, you could make unlimited amounts. So I think now because of these big advances that were coming in the DNA. You know, all the insulin we use medically now is made in bacteria using the techniques from recombinant DNA. Then people began patenting things, and there were the people who thought patents are immoral, and then other people just said patents are the way of life. And if you don't get a patent, someone else will get a patent on your ideas. You better get it. So, you know, every once in a while we make some discovery at Cold Spring Harbor which, you know, has commercial implications. And generally they're exploited by some pre-existing company, but we have dreams, you know, that will, you know, help produce some very important medicine through, you know, DNA technology. I think for the most part you don't get anywhere if you say your real aim is to just make money. You really have to say we want to produce something useful which will really advance society. And then if you do something which society needs, then you get some money. But I think you have to remain focused for the most part on science.